Today, we're jumping into statistical modeling, specifically how to handle regression when your data changes over time. Think trends, think seasonality. And our mission for you, listening in, is to really grasp the core theoretical ways analysts avoid, well, frankly, getting garbage results when dealing with trending data.
Exactly. It's all about avoiding this massive trap called spurious correlation. You see it so often in time series. If you have two things just generally going up over time, maybe it's inflation, maybe population growth, could be anything. You can easily find a statistically significant link between them. The stats software will flash lights, give you tiny p-values.
But it means nothing, right? The examples are almost funny when you see them laid out, like trying to correlate pollution levels with the number of police officers in a city that's just growing.
Right. Or the classic seasonal one, linking ice cream sales to, say, harmful algal blooms in the summer.
Both will show up as statistically linked.
Highly significant. But it's just nonsense. The real driver is something else entirely. Population pushing up pollution and police numbers, or warm weather boosting ice cream sales and algal blooms. It's not causal. Our job is to find methods to strip away that shared temporal pattern and see if there's anything real left underneath.
And that real state, that's what statisticians call stationarity, isn't it? Before we dive into the methods, maybe a quick refresher on why stationarity is so important for regression.
Absolutely. Stationarity is key because it means the basic statistical nature of your data, like its average value, its variability, doesn't systematically change over time. A stationary series tends to bounce around a constant level. That predictability is what makes standard statistical tests reliable.
And if it's non-stationary? If it's trending up or down or the swings get wider and wider,
then all the standard assumptions of regression just fall apart completely. Yeah. Your results, your significance tests, they become unreliable.
So all the methods we're about to discuss are essentially ways to take messy, non-stationary data and transform it into something stationary we can actually work with.
Precisely. That's the goal.
Okay, let's get into it. Imagine we have two trending series. We suspect they might just be trending together, not truly related. What are the main approaches if we don't know the underlying process? Let's start with trends we think are kind of predictable, deterministic.
Right. So if we suspect a deterministic trend, something systematic like a straight line increase or maybe a curve, over time, there are a couple of ways. Method one is probably the most direct. You just include time itself as a variable in your regression model.
You literally add a column that goes 1, 2, 3, 4.
Exactly. A time index.
And the thinking behind that is?
The theory is that this time variable will soak up all the influence of that systematic trend. It accounts for the general upward or downward movement. By doing that, it lets the coefficient on your actual variable of interest show the relationship after accounting for time.
Okay, that makes sense. But it feels a little strong, like you're imposing a very specific mathematical shape onto the trend. What if the trend isn't quite that neat?
It's a fair point. It does assume the trend follows a predictable path, which leads us nicely to method two, using deviations from the trend, or residuals. Still dealing with deterministic trends here.
How does that differ?
Instead of throwing time into the final big regression, you first model a trend for each variable separately. Then you calculate the residuals. That's the difference between the actual value and the value predicted by the time trend. It's basically the wiggles around the long-term trend line. You're regressing the short-term fluctuations against each other, having removed the shared long-run deterministic movement first.
That feels maybe a bit cleaner. You're isolating the short-run relationship after stripping out the assumed trend from both sides?
Many analysts prefer it for deterministic trends for that very reason. It focuses the final analysis just on those stationary detrended components.
Right. Now, what if the trend isn't this nice predictable path? What if it's more random?
Think of it like this. A deterministic trend is like a train on a fixed track. A stochastic trend is more like, well, the classic example is a random walk. It generally moves in a direction, but each step is random. There's no fixed path it's returning to.
Like stock prices, maybe? Or exchange rates? They drift around.
Exactly. They have what we call a unit root. For these kinds of trends, trying to fit a simple time variable usually doesn't work well. The standard approach is method 3, using differenced series.
Differencing. Okay, what does that involve?
It's simple conceptually. You transform the series by looking at the change from one period to the next.
So instead of modeling, say, the total national debt, you model the increase or decrease in debt each year.
Precisely. Or the change in a price index, not the index level itself.
And why does this work for stochastic trends?
The amazing thing is that for many common types of stochastic trends, this simple differencing operation transforms the non-stationary series into a stationary one. If the original series was trending randomly upwards, we call this integrated of order 1, or I1, The different series often becomes stationary, I0. Once it's stationary, you can use standard regression methods on the difference data.
Is it always just one difference? Subtracting the last period?
Usually, for series that look roughly linear in their trend, first differences. If the series looks more like it's accelerating, like a parabola, you might need to take second difference. But first differencing is the most common.
Okay, let's quickly recap part one. We have trending data, which is dangerous for standard regression. If we think the trend is deterministic, we can either put time in the regression, method 1, or regress the residuals after detrending each series separately, method 2.
Right.
If we think the trend is stochastic, random, we usually difference the data, look at the period-to-period changes to make it stationary, method 3. And the absolute wrong approach is just ignoring the trends and regressing the original levels.
That's the path to spurious results. Avoid it.
Okay. But now, let's throw a wrench in the works. We focus on trends being a problem, something to eliminate because they cause fake correlations. But what if two non-stationary trending variables should actually be related in the long run? What if economic theory, for instance, tells us they move together over decades?
Now you're entering a really fascinating and important area of time series econometrics, co-integration.
Co-integration. Sounds important.
It is. It describes a situation where you have two or more series that are individually non-stationary. They each have a stochastic trend, they're I1, but they share a common long-run path. They wander off, yes, but they don't wander infinitely far away from each other. They're linked, tethered, in a statistical sense. This implies there's some kind of long-run equilibrium relationship pulling them together.
Can you give an example?
Classic economic examples might be consumption and income. Both tend to drift upwards over time stochastically. But theory suggests they shouldn't drift completely apart. There's a long-run relationship. Or maybe short-term and long-term interest rates.
Okay, so individually they look non-stationary, but together they exhibit some stability. This sounds like a really crucial concept for macroeconomics or finance.
Absolutely fundamental. And the development of these ideas, primarily by Clive Granger and Robert Engel, was so significant it earned them the Nobel Prize in Economics back in 2003.
Wow. Okay, so what's the core idea? How can two non-stationary things combine to be stable?
The theoretical insight is that even though each series is I1, there might exist a specific linear combination of them that is actually stationary, I0. That specific combination represents the long-run equilibrium relationship. The deviations from that combination are stationary, meaning they always tend to return to zero.
So if we suspect this long-run link exists between our non-stationary variables, how do we actually test for it? And how do we build a model that respects this link?
The standard approach, especially for two variables, is the two-step Engel-Granger method.
Okay, step 1.
Step 1 is detection. And this is where it gets clever. You actually start by doing the wrong approach we warned against earlier. You regress using the levels of the data.
Wait, the bad approach.
Yes, but you do it for a specific reason. You ignore the coefficients from this regression. They're likely meaningless, spurious. What you care about are the residuals from this regression.
The errors, the difference between actual y and the y predicted by x in this potentially dodgy regression.
Exactly. The crucial step is then to test whether these residuals are stationary. You use specific statistical tests for this, like the augmented Dickey-Fuller test.
And if the residuals are stationary?
If those residuals are IO0, meaning they don't have a unit root, they don't wander off forever, then bingo. The original series are co-integrated. They share that long-run relationship.
That's really neat. The failure of the regression in terms of its coefficients actually tells you something profound through its residuals. The fact that the error term doesn't drift away means the variables are anchored to each other.
Precisely. The stationary error term represents the short-term deviations from the long-run equilibrium path. It always gets pulled back to zero.
Okay, so that's detection. We found co-integration. What's step 2?
Step 2 is modeling. If you've confirmed co-integration, you then build what's called an error correction model, or ECM.
Error correction model.
Yes. And the key is that you incorporate those stationary residuals from step 1 into this new model. Those residuals now become the error correction term.
What does this term do in the model? Why error correction?
It captures the dynamics of returning to equilibrium. The model typically includes the differenced variables, like change in y and change in x, which we know are stationary, and also the lagged error correction term. The coefficient on this lagged error term tells you how much of the previous period's deviation from equilibrium is corrected in the current period.
So it explicitly models that pull back to the long-run path we talked about.
Exactly. And here's the beauty of the ECM. The entire model is specified in terms of stationary variables.
So because everything in the ECM is stationary.
Standard estimation techniques and hypothesis tests are valid again. You can trust your t-statistics, your p-values, your r-squared in the context of that ECM.
That's the payoff. You acknowledge the non-stationarity, you find the hidden long-run link through co-integration, and then you build a model, the ECM, that respects that link while using only stationary components, making your final analysis statistically sound.
That's the essence of it. It allows you to model both the long-run equilibrium and the short-run dynamics of adjustment around that equilibrium.
Brilliant. Is the Engel-Granger method the only way?
It's the classic two-variable approach. If you have more than two variables that might be co-integrated, things get more complex. You might have multiple co-integrating relationships. In that case, analysts typically turn to a more advanced technique called the Johansen test. But the core idea of finding stationary combinations remains.
Okay, let's try and wrap this up. We began staring into the abyss of spurious correlation, finding patterns and trends that aren't real. We saw three main ways to tackle that if we don't suspect a long-run link. Add time to the model, use residuals from detrended series, or difference the data to achieve stationarity.
Depending on whether you think the trend is deterministic or stochastic.
Right. But then we explored the really interesting case where non-stationary variables are supposed to be linked long-term co-integration.
Finding that hidden equilibrium.
Using the Engel-Granger two-step to detect it by testing the residuals of a levels regression and then modeling it with an error correction model that uses only stationary components.
Which brings us back to valid statistical inference.
The big takeaway seems clear. You absolutely cannot ignore non-stationarity in time series data. You have to diagnose it and address it using one of these theoretical frameworks.
Absolutely. Whether you're looking at economic data, climate trends, medical statistics, whatever it is that evolves over time, understanding these concepts is fundamental to drawing conclusions that actually mean something. Distinguishing real relationships from mere temporal coincidences is, well, everything.